Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Noor Aldeen Alawad. Today I'm going to talk about subroutines to give more details and examples for how to write assembly language uh, for subroutines to enhance your understanding and readability of the um, last slides in the lecture. So, what is subroutine? Subroutine is a small block of instructions that performs a specific task. So, you use subroutine to get rid from repeating code multiple times. So, instead of writing or repeating code multiple times, you define it once and call it whenever needed. So, subroutine linkage refers to how executions jumps to the subroutine and returns to the main program. So you can see here that in this example, it shows the main program that loads values x and y, calls a subroutine named sh4, okay, to shift each value left 4 times and then returns. This is shift left. So this is just an overview about this subroutine. We will go through the subroutine in details now. So first of all, you know from the previous lectures that org 100, this means that the program starts at location 100. The first instruction in this location is to load value at x. So load the value at x. You can load x here, which contains 1, 2, 3, 4, and load it into the accumulator. Then after that, we have this instruction in 101, which is branch to subroutine named as sh4. This subroutine starts from 109 and starts in location 10f. You can see that the location here are written in hexadecimal. So it starts from 109 to 10f. So this procedure, which is named as sh4, you can see that this is the first instruction and this is the last instruction in order to go back from the procedure to the caller. So this instruction, you can read it like this: branch to the subroutine and store return address. Branch to subroutine and return and store the return address. So after accomplishing this subroutine, you can see that I will not now go to subroutine in details, just you can see that after returning back from the subroutine, you store the value in X. So we have the value 1, 2, 3, 4, and we have a new value that will be stored in the accumulator, in the stored from the accumulator into X. So the accumulator that contains the shifted value and will be stored in X again. So X will be now contains the shifted value of itself. Then again, the process will be repeated for Y. Load Y from this location, which contains 4321, and then branch to subroutine sh4 again, shift the value, shift the bits four times, and then go back to the caller and store the shifted value in Y. Then the program will finish. You can see that here we have halt. So in the program, now with the values that will be shifted are x and y. So you can see that in summary, the procedure or this program will start from 100, loading the first value, then shift left the value in this variable 4 times to the left and store it at the same memory location. Then repeat that for the second one. Load the second operand, which is 4321, and shift the values 4 bits to the left, and then store the shifted value in y again. So x and y, instead of having these values, will have the shifted values of themselves, x and y. So then the program will finish. You can see that this procedure is called 2 times. You can see that it is called in 101 and it's called also in 104, 101 and 104 for the values of the operands x and y respectively. So we will go deeper now to see how this procedure works. In location 109, you can see that we have SH4 HEX0. Here we can see that this stores the return address. When the procedure finish, then the return address will be stored here to go back to the caller. So it will be used indirectly by the end of the procedure. You can see here in 10F branch unconditionally to SH4 indirectly to the return address, the address that will be returned to it after executing this procedure, which is here 101. After we finish, we have the return address that is stored in the beginning of the procedure here. So here we have stores the return address. You can see that in the previous examples that when we sum two values, then we can have the label sum hex and 0 or decimal 0. This means that after finishing the operation of addition, we store the value in sum. In this memory location, which contains 0, will be replaced with new value. Same scenario here. Instead of having this 0, that return address will contain the new return address after executing this procedure. So we will store here the return address, and we have circular left shift for the accumulator 4 times. You can see 1, 2, 3, 4. So when make this circular shift 4 times, then after that, the value in the accumulator, which contains the value, let's see that the first call is X. So this 1, 2, 3, 4 will be shifted 4 times to the left, and after that will be masked. You can see that will be masked like this with 0. FF will be, and the I mean that the value of X will be applied, we will apply the shifted value of the X, and the mask will apply the AND between them. So the mask here contains F, 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 and 0. You can see also, or you already know that 0 and anything, it will results in 0. So this will, I mean that turning the values or the upper you can see that you can turn the values from 13 to 16, in location 13 to 16, the accumulator to 0. So it will mask the upper bits of the accumulator to be 0. Then we have, after finishing the procedure, we will return to the main program. You already know that branch unconditionally to SH4, which contains the return address that will be back to the caller here, which is in location 101. This will be repeated also for the other one, which is Y. And you can see here, I already write here that some calculations. When we shift left this value 1, 2, 3, 4, it will be 2, 3, 4, 0. You can see that 2, 3, 4, because the one will be shifted circular left, it will be here. The one will be, I mean, like this here. Then will apply and with this value, it will be 0, like this. So it will be 2, 3, 4, 0. So 1, 2, 3, 4, it will be 2, 3, 4, 1, and FFF0. The F are all ones, so the AND with these ones, it will be the same value, and the AND with 0, it will be 0, so the 1 will turn into 0. So 1, 2, 3, 4, it will be like this. 1, 2, 3, 4, it will be shifted, circular shift like this. 2, 3, 4, 1, and FFF0, it will be result into 2340. Same thing for the second one. It will be like this. It will be 1, okay. It will be 3, 2, 1, 4. Okay. It will be like this. uh, and and FFF0 to results into 3210. Okay, so we have two values now. You can see that here. Yeah, the result is from 1234 to it be 2340, and from 4321 to it be 3210. The same that was that was written here. So this is the, I mean, this example will give you an idea how this procedure works, and it will make a circular shift for the one for it will be on the right, for on the right it will be now uh, deleted by making an add with the mask that contains FFF and 0. So F's are ones and 0 are zeros. So F 1 and the value here in the hexadecimal, it will be the value itself, and 0 with anything, it will be 0. So it will delete this one and delete this one. And by deleting, I mean that converting it into 0. This is through this mask. You can apply this mask by and. The mask is stored here in location 110. So this is an example. I mean that this is not the first and the last example about the procedures or subroutines, but to give you an idea on how this procedure is work. You can see that we have this label that start here, and this label to end the procedure in and give and go indirectly to the caller, because here we have the return address of the procedure in order to go back to the caller here. So this procedure is called 2 times 101 and 105. I shift the value of the x, which is 1234. It will be 2341, and this one 3214, and it will be ended with the FFF and 0. It will be 23 it will be 2340 and 3210. So this is an example about the procedure that is used in order to make shift left and return back to the caller. After that, the program will be finished here in location 105. Second example, it is about OR. You can see here OR. Okay, so in this example, you can see that it's talking about the subroutine parameters and data linkage. So the goal is to understand how data moves between a main program and a subroutine, and then walk through an example that performs a logical or operation using memory location. And what we are seeing here is the same logic that we already know in the previous lectures, using the De Morgan law in order to make an OR operation through make the complement for the operators, the logical and between them, and then the complement of the results. It is the like A prime dot B prime altogether prime, which will give us A plus B, which is OR. So first of all, we can see here that the location, the first is org 200. This means that the program starts at location 200. So you can see that in general, this example shows a subroutine that performs a logical OR. And to do this, we need an operand, the first operand, the second operand, a location to store the result. So these values will be stored in memory. Will be stored in memory. Just 1 minute. Yeah. Okay. So first of all, we have location 200. Load X. Load the first operand into AC. X contains this value, 7B95. All right. So X contains this value, 7B95. So load the first operand stored at memory location X into the accumulator. The location 201, we have branch to subroutine OR. We will go to the subroutine, which is here. So X and Y are memory locations, and or is the name of the subprocedure. How we can determine that? Because you can see that BSA is a branch to a subprocedure. So BSA branch, but here we have load X to go to this memory location, but here we have going to a procedure like this, which is called OR, and this procedure starts at 207, and you can see that it ends at 20F. So let's start and go through this program. When go to the OR here, this we have here hex 0. So hex 0, you can see here OR hex 0, branch to the subroutine named OR, source the return, and this is the memory location right after the subroutine code. So this here we will contains in this location the return address from the procedure. The same idea like the previous example which we have here, hex0, it will save the return address from this procedure. Also the same thing here, hex0, it will save a return address from the procedure. First of all, when we load the first operand, which is 7B95, and go to this subroutine, the first thing that X is now saved in the accumulator. So CMA, it complement this operand, which is X, make a complement for this operand, and store it temporarily in memory location, which is called TMP. Why we store it in temporary? Because we will do the same thing for the second operand. So the accumulator, it's like the idea of variable just contains one value. You cannot store it two values. So we will save the first value or the complement of the first value in a temporary memory location in order to use the accumulator for making a complement for the second variable. So first of all, we complement the accumulator, which contains the value of X, and store it in temporary here, temporary variable here. Then after that, we will load the second operand indirectly. You can see that LDE or indirectly, or we can go back from this procedure again to load the second value. So you can see that in 20A here, in order to understand the operation, loads the second operand indirectly and then complements it. The second operand is Y. You can see that we have this is the first operand, and this is the second operand, which is Y. So the second operand is 3A, you can see it 202. When you go load or indirectly, we will go here in this location, will be saved the return address, will go back to this location 201 and go to the next instruction, which contains 3AF6, which is the value of the second operand. This second operand will be complemented. You can see here, complement the second operand. And now the accumulator contains the complement of the second operand and the complement of the first operand, which is stored as a temporary variable. So here we can see that the AND operator will be applied for accumulator, the value in the accumulator, and the value in the temporary here, which contains the complement of the first variable. Then after that, we have the results, which contains the AND between the complement of the first operand and the complement of the second operand. Then we need to complement the result, which is stored in the AC. And here we increment the address again. Seek that ISC, it means that increment the return address. So execution resumes after BSA. So we go here indirectly to the caller. You can see that we came from this instruction. Okay, then the value or the result will be stored in Y. Then the program will be finished or will end execution. So after that, the results of this program is to make an OR operation. So We can just make a briefly mean an overview of about this program. Can see that load the first value x, then go to OR procedure. This contains the return address. Complement the value of x and store it in temporary. Then load or indirectly. We'll go to here, which contains the return address. The return address we will go here to the caller. The caller will increment this instruction or the counter of the program into here, which contains the next operand. Then go back here to complement this value and make an AND operation between the temp and this value, which is second operand, and the result will make a complement for this result, and then increment the return address and go directly to the next instruction, which is here, store y, and store the results here in y, which contains the result of the OR operation. So you can see that we go back and forth to OR this OR procedure more one time in order to make the OR operation. Next, we have this procedure. This procedure, you can see on the right, I already explained to you in the lecture that this is a program written in Fortran language. It consists of procedures called MVE. So this procedure have inputs like this: a source list and destination list, and then we have n, which contains the values that will be um, copied or moved from one block to another block. So dimension mean that's like the meaning of arrays in Java. So we have two dimensions or two lists in like in Python, source of n that with size n, both of them. So these are two parallel arrays. We saved the values from source into destination. So this is do loop, the same idea like a for loop that iterates from 1 to n in order to copy the values from source of I to destination of I one by one. So you will think in assembly that you need counters and pointers in order to pointers for getting the values or of from one location to another location, and counter to count the memory cells, I mean, or the elements of these lists. So now we can take an overview about this program like the following. So the main program contains three main parameters. You can see that we can go to this subroutine, which is branch of subroutine MVE, and we have the first address of the source of data is 100, and the address or the first address of the destination data is 200. This means that copying from one list to another list, and the size of these lists is 16. You can see that decimal minus 16. This means that the number of items to move are 16. And you can see that when we increment the counter inside the procedure like here, we will go outside from the loop or end the loop when it will be 0, and then finish the program. So starting the address of the source block, you can see that it is 100, and the starting address of the destination block is 200. The number of items are 16, or the number of items 16, and we have branches to the subroutine and saves the return as. This means that branch to this subroutine MVE and save here the return address in order to go back. So you can see that bring address to the source LDE MVEI. You can see here LDE or I. This means that go to the next instruction after the calling, after the caller jumps to callee. This means that here you can see LDE or I. This means that go to this instruction 202 after the call. You can see here LDE MVEI. This means that go to the second instruction after the call, which is HEX100, and store it in PT1. Okay, this is the PT1 contains the address of, or the first address of the source data. Then increment the return address. I mean that the return address now, it will not be here. The return address will be the next instruction. So we are here, then we will be here after increment return address. You can see. Then load MVI indirectly. This means that go back to this label and jump to the return address. The return address now, it is not the first, not the caller address, not the next instruction. It is the instruction that follows it, which is HEX 200. So store this 200 into PT2. Now PT1 contains 100 and PT2 contains 200. This means that PT1 contains a pointer to the first block, and PT2 contains a pointer to the second block. Then increment the address again. It will be now pointing this address, or return address will point to decimal or DEC minus 16. Then this value, it will be loaded again here. You can see that it will be stored after loading this value. It will be stored into CTR, which is called the counter, and then increment the address will be go to HLT. This means that will not be now executed, just to be incremented in order to finish the program. But here we have loading the first pointer indirectly and then store it in PT2. This means that load the source item and store it in the second source item, I mean destination item. So the source address is BT and destination address is stored in PT2. So this is the source address, which is stored in PT1, and this is the destination address, which is stored in PT2. And CTR contains the number of items. So here we have loop. You can see that LOP, loop, whatever LP, which is a label that starts here and ends here. It will be repeated 16 times because we will increment all the time. We will increment three variables, which are BT1, BT2, and CTR. And the one that will give us control over the loop in order to go out from or exit from is CTR, which is minus 16, and it will be incremented one by one until it will be 0. So this means increment and the skip of 0. When it will be 0, I'll go outside from the loop and end the program. So load the first one indirectly and store it in the second destination, or this destination pointer here, and then increment both pointers and the counter. This means that load from the first element. I mean that, like an example, if we have an array that contains 1, 2, 3, and here we have an empty array, then the first operand, which is 1, or first element, which is 1, which will be loaded into the EC, and this value 1 will be stored into PT2. I mean that the first element of the second list. Then will be increment the two pointers and increment also the counter. So the pointer will point into what's called, let's see here, 1, this is 2, and this is 3, etc. So this is the source, and this is the destination. So this value will be loaded into AC and then stored here. I'm talking about this. Then the pointer will be incremented. This is about PT1, and this is PT2. PT1 was here, and PT2 was here. Now after the two increment will be, let's see in another color. Now BT1 will be here, and BT2 will be here. And the counter CTR was minus 16. It will be after increment minus 15. Then PTR1, PTR2, and then branch to the loop again. We will not exit from the loop because this value is not 0. Will we reach and will reach 0, we will exit. So same thing. This will be go to AC and then saved from the AC to the second element, etc. until we finish the element number 16 here. So the value will be saved at the last element of the destination uh, uh, array or list, and then the counter will be 0 and we exit. Now we exit from the loop and the branch again indirectly here, which will give you control to the return address here, which is saved from this instruction, and exit from the program. Okay. Let's go now, or maybe we can make a summary, short summary. So in each iteration, the value will be loaded from the source pointer and stored in the destination pointer, and increment the pointer PT1 and increment the destination pointer PT2. Then increment the counter also CTR. If the counter not 0, then return and loop again in the branch loop. When done, the subroutine returns to the caller using branch move indirectly. Okay. The Fortran equivalent source code, which is on the right, I already explained at the beginning of the explanation. Now we will go to the next slide. We will talk now about the how to deal with input and output. You can see here that this example is about input and output programs. So show two simple assembly language routines, one for reading a single character from the input device and another for displaying character on the output device. So these examples illustrate how basic computer architecture interacts with input and output to check device readiness and move data in and out of memory. So this is about input and this is for output. You can see here that I will make this block here and explain it to in order to know what is going here. So here we have a label. Forget about the name CIF, but it is descriptive name, right? So check input flag, which is written here. So this is a label. You can write any label you need to write or you prefer to write. And here we have this is the instruction which is about checking the input. So SKI, check the input flag. Check the input flag. So if the flag is 0, so a branch again. So if it is 0, I will go here again to check. If it is 0, I will go here to check again. If it is 0, I will go here to check again. I mean that I will be in a loop all the time. If checking the flag and it is 0, I will check all the time until it will be 1. So if the flag is 0, branch back to check again many times until the input device give you permission to input the character. When it will give you the permission? When the flag will be 1. If the flag is 1, then we can input the character and output the character to the display or to the output, I mean to the screen. So display to ensure correctness. And you can see also here store CHR, I mean that the just to echo this character to see it on your display, you can store it on a variable in order to display it on your console. So here we can see that this procedure, which you can see here, is used for checking for input, and this is for input characters which contains 1 byte. And all the time I'll check for the readiness of the input device until it will be ready and the flag will be 1. Then input this character and output again them on the screen. Another program is the to output a character. You can see that in the same scenario exactly. You can see here that this is the procedure. This is the loop. Sorry, this is the loop. For this loop, you can see that. Okay, you can see that. Okay, let us erase them all. Okay, now here, load the character. You can see here that we can load the character. This is character from here. This is the character which is W. W represented in hexadecimal as 57. It will be loaded into accumulator and we will display it on the output device. Now, we can display it on the output device if the flag is 1. If it is 0, we will stuck in this loop. Branch unconditionally to check output to flag and check this output to flag. If it is 0, still we will be in this loop stuck until the flag will be turned into 1. Then after that, it will be it will be displayed on the screen and the program will stop. So this is for input and this is for the output. And you can see that their ideas, maybe they are the same, that we have label, we have an instruction which is check for the input and another instruction for check for the output. While the flag is 0, we will stuck inside the loop until the flag will be 1. If it is 1, we will go outside from the loop and maybe we can see that input the character or output the character depends on the logic of the program. Okay. I think that this is the last slide. Yes, this is the last slide. The last slide, it's talk about how to back two characters together. You can see that into one word. The word in memory consists of 16 bits, 2 bytes. You already know this information before. Word consists of 2 bytes, which is 16 bits. So if we have two characters together packed, they forms a word. So this procedure is used to pack two characters together. So if we back two characters together, we think about it and before to see that, first of all, we need to make room for the second character to be backed beside the first character. So if we have, I can explain to you the idea here. If we input A and we will back B with A like this, okay? You can see again. This is pointer options, okay, eraser. You can see that if we have A and we will back B beside A, so here is A and here is B. I'm just adjusting the mouse. Okay, so this is A and this is B. They are back together to form a word. Word consists of 2 bytes. 2 bytes, which means that 2 bytes, which means that consists of 16 bits. So we need here to make space for B. Because we have A, we need to shift A to this place. I mean that we need to make a room for B. B consists of 8 bits. These bits should be 0 in order to put B instead of these 8 bits. So we need to shift A 8 bits to the left in order to make here zeros. This is 4 zeros and again four zeros. So we have eight zeros. If we shift A to the left 8 bits and put zeros on the right, then we can have now room for B or space for B. So after that, we can pack B with A to form a word. So this is the procedure that use this strategy in order to pack two characters together to form a word. So first of all, you can see that into you can see that this is the subroutine entry, start from into. Then we have, first of all, we have FST, we have SKI, check the input, and the branch FST. As before, you can see that this one is used to check for the readiness of input. If the flag is 0, you're stuck here. If it is 1, you will go and input the value from the keyboard, which is here in our case as an example is A. So if we input A, then output A, we can just make an echo. This is not necessary, but just to ensure that we already input the character in the right way and displayed on the screen as A. Then we have this call for the procedure SH4. You remember this procedure we talked before? This one. SH4, which is this one. You remember? We already know in the lecture, also on this recording, that this procedure is used to shift the bits to shift the bits 4 times to the left. So circular shift the bits 4 times to left. So here the same thing. We shift it not just 4 bits. We shift it 8 bits, but we don't have 8 bits in the procedure. So we call the procedure 2 times. So the value that is stored in the accumulator, which is A, will be shifted left 4 bits. It will be A and 4 zeros, and then shifted again. It will be A and 8 zeros. So after that, A and 8 zeros in order to put the B beside A. So after that, we have just, you can see that this another label SCD, check the input. And this is so read in order to read B. So here we read A and display it, then shift it to the left 8 bits, and then on the right will be 8 zeros. Then we read B when the input device is ready. Okay. Then we output the result. So input a second character, then output the result. The results will be, if A and B, it will be like this. A, and when we read B, it will be B beside A. Then branch in I, this means that going to this one, this label, which contains the return address from the caller, the program that calls this procedure. So to summarize, you can see that this subroutine demonstrates how to wait for input, which is in the FST SKI, then branch FST. The same thing for SCD, then branch SCD, for to reading 2 characters, and use logical shifts for 2 times and back the 2 bytes into one board, and return cleanly to the main program, which calls this subroutine. So this is an example how to pack two characters together to form a word in memory which contains 2 characters. We use a subroutine 2 times, and this is the usefulness of using subroutine, that you are not required to write the whole code more than one time. So just one time and call it many times. And you see that in high level programming languages, we always use subroutines and functions in order to um, employ the reusability in our codes and make it more efficient. Hope that you understand every idea in this video, and I hope that you will get high results in the final exam. And thank you very much. شكرا جميعا ويعطيكم العافية. والسلام عليكم ورحمة الله وبركاته.